So as I was saying earlier, the parameter alpha is, we call it the step size. And typically in machine learning, we call it the learning rate. When we are trying to minimize the loss function, that's the name that we refer to. Now, as you will see, as you progress in this class, it could be fixed. I mean, we take the same size step every iteration, or it makes sense that we can reduce it as we get closer and closer to the optimum to avoid overshooting the minimum. So we can decay it with some methods. So there are many different ways to set a schedule to reduce the learning rate as the algorithm converges to the optimum. So for univariate regression, we know that the loss function is quadratic. We've seen the function before, which is y minus hw squared. So it's a quadratic function. So the partial derivative will be linear. Okay, so essentially the only thing we need to remember here is just the chain rule, essentially, which is the partial g the partial z of f partial x is g prime of f times partial f partial x. So that's essentially the only rule we're going to need from calculus to apply that here. So let's take the derivative then, because we can do that here. So partial w of y minus h squared is going to be 2 times the parentheses, which is y minus h of x, times the partial derivative of the parentheses, which is partial wi of y minus hw of x. So this simplifies to, if I plug in the expression for hw, it's w1x plus w0 for univariate regression. So now I can use this expression to evaluate the partial derivative with respect to w0. So with respect to w0, of course, the outside part is the same, and you can see here the partial derivative with respect to w0 is just minus 1. So it becomes negative 2 times this parentheses. And now if I replace wi with w1, I get, again, the partial derivative in that case is x. So it becomes negative 2 times, negative x. So it becomes negative 2 times y minus hw times x. So these are the two partial derivatives that we need in order to apply our algorithm here, the gradient descent. So let's recap then. We have a learning rate that we pick ourselves, and then we're going to start at some point, w0 and w1, random point, and then we're just going to find the next value for w0 by, remember we multiplied by negative of the gradient, so it becomes plus, and the gradient was y minus hw, and we sum that over all the data points. And for w1, we just multiply yj minus hw times xj. So the only difference between the two summation is that inside the summation we have to multiply by xj, which we know, of course, which is x at every data point. By doing this iteratively, we w1 and w0 will get closer and closer to the optimum. So notice that if h is bigger than y, this means that our prediction is too high, right? If h at any point is bigger than y, the prediction is too high. So we need to reduce w0 a bit, right? Because that's going to be negative. So that's going to take W naught, the next iteration is going to be less than the one I started at. And reduce W1 if X was positive input, because W1, if again, we had a prediction that's bigger than Y. If X is positive, this means that we have to go down a little bit. So W1 will come down. So the net effect is that our next prediction will try to be lower than Y, right? Because we started with a prediction that was too high, and now we're going down, so our next the weights are going down, so our next prediction will be lower. And vice versa, of course, if the error was on the plus side, so sorry, on the negative side, so you had Yj bigger than H of X, so this means that your prediction was too low, so you need to increase your weights a little bit. So again, you're going to see that you're adding a positive term to W0 and W1. So you're making them bigger in the next iteration. Okay, now, and the reason why we can use summation here is that because the derivative of a sum is essentially the sum of the derivatives. Okay, so we can easily apply that here and just take the sum over all the data points. Now, this approach is called batch gradient descent. Okay, and the reason why it's called batch gradient descent is because in order to take a step in your algorithm, you have to calculate the gradient over the entire batch, over the entire training data, because this summation is performed over n training points. Okay, so we can only move to our next estimate after we evaluated these two summations. As you will see, there are ways to speed up the process. So say if we have a million data point, we don't want to wait until we evaluated a million summation over a million term before we take our next step. We want to speed up the learning process a little bit. So there are ways that we will discuss, which is essentially stochastic gradient descent. Let's start with that. So remember also we said that the loss function is convex, which means that in the case of univariate regression, there is no danger of this algorithm getting stuck in a local minimum, and we are guaranteed that it's going to converge to the global minimum. Okay, only in this case, only in the univariate case. Okay, of course, that's as long as you pick a reasonable learning rate alpha. Otherwise, if your learning rate is too big, then you're going to overshoot your optimum and you might never converge. Now, just make sure you don't pick it too slow as well, because if you pick it too slow, you're going to converge very slowly. So we'll have, and that's why a lot of studies have been done on how to pick the learning rate, which is essentially the most important parameter in machine learning, is how fast you learn or how you change your learning rate as the learning process is applied. You don't want too slow and you don't want too fast. So how do we deal then with the problem of having to evaluate this summation over all training points, which could be very large, maybe too large even to fit in the processor memory, and poses a lot of problems. Oh, another term you're going to hear a lot in this class is epoch, which is essentially when you covered all the training examples. So essentially here we say that the update is done after every epoch. Okay, so when the algorithm have seen all the training examples. So a faster way to do gradient descent is to use what's called stochastic gradient descent. And in this approach, we randomly pick a small number of training examples at each step. So if we have a million data points, we don't really need to evaluate the function at a million data point to know what way, what direction the next step should be. We can just pick 10,000 random points, evaluate, the summation over these random points, and take the step in that direction. So the original version of stochastic gradient descent selected only one training example from each step. But people realize that, okay, this is too extreme to pick just one random point out of a million points and evaluate the gradient there. So we found a happy medium, which is called mini batch, okay, which essentially allows us to select m sample out of the n total training examples, okay. So instead of picking one, we're just going to pick m. And for example, if we have 10,000 training examples, we can select a mini batch size of 100. Then on each step, we have reduced the amount of computation by a factor of 100, because 10,000 divided by 100 is 100. But because the standard error of the estimated mean gradient is proportional to the square root of the number of examples, the standard error increases by only a factor of 10 by doing this approximation. So even if we have to take 10 times more steps before convergence, mini batch stochastic gradient descent is still 10 times faster than full batch stochastic gradient descent in this example we just discussed. Okay. Just one more point about stochastic versus batch gradient descent is that with some CPU or GPU architecture, we can choose M to take advantage of parallel vector operations. Okay, so we don't have to evaluate these gradients in series. We can actually split the job between different threads, and this makes it much faster. Making a step with m examples n becomes almost as fast as with this example. Okay, that's where the power of GPU comes in, is in being able to parallelize this algorithm. Okay, the ability to evaluate these gradients using parallel architecture of the chip. Okay, with these constraints, then m becomes a hyperparameter. Okay, that should be tuned depending on the computer or the resources you have access to. Now, convergence of mini-batch stochastic gradient descent is not strictly guaranteed. It can oscillate around the minimum without ever settling down on it. Okay, but as we will see later on, if we implement a schedule to decrease the learning rate, so that will allow us to guarantee convergence. Okay, we don't have to worry about this. Also, stochastic gradient descent can be helpful in an online setting where new data are coming in one by one. Okay, and in this case, it's called online gradient descent. So these are all features of stochastic gradient descent, and let's move on then to multivariate regression.